Hi, everyone. I'm Muneeb, co-founder of Blockstack, and really excited to be here today because I actually worked at SICS for like over 3 months with Timo, who's sitting right here, and that was exactly 12 years ago. So in a way, my research journey kind of started from this place, and I'm really excited to be back. Uh, as you heard, that my background is basically distributed systems. I did a PhD at Princeton, and towards the end of it, I actually took a leave and started a company which is more like an open source project. And we've been doing that for around 4 years now. So today I'm going to talk about that project. It's called Blockstack, and it's basically a new decentralized internet, and we're going to jump right into it. So I know that this sounds extremely ambitious, that you are building a new internet, but the good news is that we have already built it, right? You can actually go and start using that. And by that, what I mean is that we're not reinventing the entire stack. If you think of like the internet stack, what we have done is we have roughly trying to replace the top half of it, right? So we do use TCP/IP, although we don't need to. You can actually use some other types of communication protocols as well. But we are really trying to replace the upper layers, like things like the domain name system, things like public key infrastructure, things like how cloud storage works and where applications run. So today you can actually just go to Blockstack, and we have a developer version of our browser, and you can download that, and in that browser you would actually connect to this second new internet, meaning that you're no longer talking to the traditional domain name system, meaning that the way that websites are loading and how authentication is done is very, very different. So what I'm going to do in this talk is like, first I'm going to go over like what are the problems with the current internet, what we call the traditional internet, and why did we start off with Blockstack, and basically what's the new architecture, right? So I know this is a technical audience, so I'll go into some of the technical details as well. And for people who are not familiar with blockchains, I have some background information for that as well. So problems with the traditional internet. People who are familiar with the end-to-end design principle, this is a really famous flagship design rule for the internet by David Clark and others, and they basically said that don't keep any complexity in the middle of the network, right? So all of the complexity should actually be at the edges, at the clients, right? So the internet itself was meant to be a very dumb network, and in many cases it still is, right? Like if you look at the basic packet transfer, like the internet doesn't even know like what data it's really transferring. It's basically sending a packet from point A to point B, and that's it, right? And the rest of the stuff is actually kind of like built on top of this very simple interface of just transmitting data from point A to point B. But what started happening was that you would see that initially people thought that there will be clients who would just be talking over this network, right? But we started seeing services being developed on the other side, right? And these services started becoming more and more and more and more complex, to the point that almost like this thing now is like a dumb terminal. Like you can't even do anything useful if you don't connect to the cloud services. All of the state, all of the applications, all of the data, they're basically just living on the other side with the cloud providers. And then there are many problems with that, right? So if you look at, I'm not picking on Facebook, but just like one example of a service provider, Facebook would basically keep all of the user data, right? They would build out some sort of an authentication service, so you're completely dependent on like whatever type of authentication they have, and you are trying to prove that, hey, this is actually me, please give me access to my own data. And if you're trying to connect to Facebook, the first step is usually you do a DNS query. Again, like if you're doing a DNS query right now, you don't even know what server you're talking to, right? So in a way, you're just blindly trusting whatever result you're getting back, that this is the correct Facebook, and then people see this green lock sign that makes them feel good, that okay, this is secure, I am actually like talking to the right Facebook. And in most cases, it's actually one company, VeriSign, right? VeriSign is saying, trust me, you are actually connecting to the right source, which may not be true. And so, like I know it's not a company. It is more like a federation, but still, it's a centralized source of the ultimate truth of what is there in the root servers, right? If someone can actually tamper with that data, they can basically change everything, all the mappings that are there. And so we are reliant on these root servers. We are reliant on these companies that actually manage them. And same with the public key infrastructure. And problems do happen. Like with DNS, there are all these documented attacks where someone messes up DNS information somewhere. This happened in 2010 in Chile, where they were actually picking up DNS data from China, and China was trying to block certain things, right? So now another country, you cannot access certain sites in a different country because China was trying to block something, right? So these are signs that kind of like point to that something is wrong with this system, right? That people shouldn't get impacted like this based on the way the internet is actually designed. Similarly, with certificate authorities, recently there was a case where Turk Trust, a certificate authority in Turkey, was actually issuing the wrong certificate for Google, right? So imagine that if you're in a country, an entire country could be thinking that, hey, this is the right Google or Gmail even, and it might be a malicious actor, right? So they revoked the certificate pretty quickly, but this happened. And that just shows you the kind of power these certificate authorities have, which are these centralized services, and we just blindly trust them, right? So that's kind of like the first problem where if you look at like David Clarke's recent work over the last like 10, 12 years, he started talking about this thing called a trust-to-trust design principle, right? And so David Clarke is like looking back at the original design of the internet and is basically saying that we didn't explicitly thought about security, right? Security should have been at the edges as well. We left these like trust points in the middle of the network, and in his updated principle called the trust-to-trust design principle, he's effectively calling that out and saying that the connection between two users should be between my trusted zone and the other person's trusted zone, and you should not trust anything in the middle of the network, right? We kind of like, in my PhD thesis, I kind of like took that general principle and took a deeper dive on that, right? So we actually built out a full architecture for how this trust design principle could actually work in real life. And with the open source project Blockstack, we have an implementation that is working today. So with this principle, basically what I'm saying is, if I trust my laptop, then it should be possible for me to do all my lookups, all my connections, without trusting any other device on the network. And this is a really hard requirement if you think about it, right? Because like, how is it possible that you can independently verify every single thing on your own machine, right? So we'll look into like how that can be done. So the second problem is what I talked about earlier about this remote storage. Like over the last 10 years, people were really excited about cloud computing, and what we have realized now is that, oh, suddenly we just don't have any of our data ourselves, right? And we are just blindly trusting these cloud service providers, not just with the data, also with the application logic. Like imagine that if you're running even a word processing software, you're not even running that locally. Most of the time, it's like Google Docs or something running in a cloud server somewhere, and if that app wants to be malicious, or if that app is giving different views to different users, they can completely do that. They have 100% control over what that application is and how that application actually runs. So the second problem is that the user data and apps, like they're not in users' trust zone anymore, and this is something we want to change. We want to move to a model where you download software and you can actually verify that this is the right software that you wanted to download, and then you run that software locally. So for this, we basically boiled down this decentralized internet stack to decentralized DNS and public key infrastructure, and then more importantly, the decentralized storage and discovery mechanism. So how do you discover user data, and how do you have a fully decentralized storage system that you can actually use? So now I'm going to give you a background on blockchains, and the reason is that blockchains are used in this architecture as the initial discovery layer. Blockchains are the kind of like the mechanism through which you don't trust anyone else, and you can independently verify certain key pieces of information before you connect to anything else. So with blockchains, like it's actually like it's a fairly complicated technology because it sits at the intersection of like distributed systems, applied cryptography, and also economics. Right? There's a lot of game theory involved, and it's a fascinating field. But if you want to simplify it, a blockchain is actually just a file. Right? It's literally just a file. You can download it, and it's append only. Right? So if my computer, let's take Bitcoin as an example network. If my computer is connected to the Bitcoin network, I will have a file on my laptop that is the Bitcoin blockchain. And whenever there is a new block announced, it's an append-only operation to that file. So the data basically just keeps growing in a blockchain, and you can think of that as an append-only log with very strong tamper-resistant properties. So it's very hard to actually tamper with any of that data, and we'll get into how that is done. So every node on the network has a consistent copy. Right? So imagine all of us, we just connect to the Bitcoin network. We'll all have our own copy of the blockchain. And as new blocks are announced, that information would sync up. Right? And all of us would end up on the same state. And I'll get into like why that happens, what that consensus looks like. So in this network, you basically work with private public keys. Right? Extremely simple. You can think of that as like this technology has been there for decades, and finally it's actually finding a really interesting use case. A lot of people have finally started using these private public key pairs and have started securing their data through that. And a Bitcoin address is actually just a public key. Right? It's actually a double hash, refers to a SHA-256 and then a RIPE MD160 off the public key. But you can just think of that if this is your private key and this is your public key, this is just a hash of the public key. Right? So it's just a different format of displaying the public key. Right? And so that's your Bitcoin address. So that's your public identifier. Right? And now you can actually associate certain digital assets on the blockchain that you own with this public identifier. And Bitcoins, the tokens, they're actually a form of digital asset. That you're saying that, okay, I have X amount of money that is represented in terms of Bitcoins, and only the person that has the private key to this account and can sign a transaction can actually spend that money. And spending money is basically proving that you are the owner, meaning that you have access to the private key, right? And then just doing some sort of a new transaction. So the spending money is just a type of transaction that we came up with. You can do any type of transactions on blockchains. So with the Bitcoin's peer-to-peer network, so you basically, let's say if you run a node right now, by default you would connect to like 8 nodes. You can increase that to like, let's say 128 or something. And it's a peer network, and it's a full broadcast network. I know that the distributed systems people sitting here are going like, what? Like, how is this going to scale? And that's why I think there are very interesting distributed systems problems in this space right now. So it's a full broadcast network. Any transaction that any node is basically hearing, they rebroadcast it to every peer that they're connected. Let's say I'm connected to 8 peers. I saw a transaction. I'm just going to broadcast it to everyone else. So all the transactions are flooded. Everyone basically sees all the transactions, all the nodes. And then what happens is that you can think of the mining process. You might have heard about this Bitcoin mining, that people are burning a lot of electricity to mine Bitcoin. That is just a leader election algorithm. Like traditional distributed systems, every time there's a consensus protocol, you're trying to elect a leader, and that leader is going to write the state for that round. And that's exactly what's happening in Bitcoin. Right? So in a round, you basically want to elect a leader, and that leader is going to write the next block. And how Bitcoin does this is that there are these cryptographic puzzles which are very easy to verify, but very hard to compute. Right? So all the nodes that are actively mining, by the way, not everyone mines. Let's say all of us connect to the Bitcoin network. A subset of us might actually want to mine because mining is a very compute-intensive process. Right? So you're actually burning a lot of electricity when you're trying to find potential solutions to this puzzle. So how that works is that this is a Bitcoin block. It has basically a hash of the previous block. You can think of these as pointers. But more importantly, it also means that this block knows that the previous block existed in time, because time is moving this way, right? So this block, anyone who's producing this block has a back pointer that is the hash of the last block, so that this person is kind of like saying, I am ahead in time, right? I already know that this block actually exists, right? And all the transactions that, let's say we were trying to send certain transactions on the network, they just get included in that block. And the writer, whoever won the round in that sense, can basically decide to include or not include certain transactions. And that's where incentives come in. That why would a miner include your transaction? Sometimes there are these transaction fees, so the miner is actually getting some money out of everyone who's trying to communicate on the network, right? But there's also this reward that is built into the protocol. Every time there's a round and a new block comes, new money is being generated. So these new Bitcoins are being generated in the network, and the miner actually gets the reward, right? So that's the economic incentive that is there for the network to basically keep running, right? And so that so let's go to this example over here. What happens is that this nonce is the solution, right? So you would take all the data and you're basically incrementing the nonce, trying to get a hash that has a particular characteristic. And that is basically the number of zeros at the start of the hash, right? So you're basically randomly computing these SHA hashes using this data, and as soon as you hit a hash, the start of which looks like 0, 0, 0, 0, 0, 0, you have a solution, right? And you would try to write a block and broadcast your solution, and everyone on the network would basically see that someone found a solution, and now they have an incentive to basically throw away the work they were doing and move over to the next block, right? Because it's the probability of people building on the longest chain is actually more, right? So sometimes you would see a fork. Let's say a subset of the network was trying to go in some other direction because someone was basically trying to say, no, I won the round and not that person. Usually, wherever the majority of the compute power is, that chain would end up being the longest. And that's the rule for consensus. That nodes always go for the fork that is longest, meaning that it is backed by the longest proof of work. More work is backing that blockchain than any other copy that might exist that is different. Right? So that's how everyone can independently verify. If I get two different blockchains, all I have to do is independently calculate how much work was done on these blockchains, and I will pick the one that has more work. And so this is kind of like just the backgrounder on blockchains, and now we will shift over to how these can be used for building other interesting things on top. So blockchains obviously have a lot of limitations as well, right? As you can probably tell while I was describing how they work, the first thing is that on this network, there's very limited bandwidth and data storage abilities, because everyone has a copy of the same data. So if I'm actually announcing a new piece of information and I'm writing it to the blockchain, that write is extremely expensive, because every single node on the network stores that data, and not just stores that data forever, right? Because you have to keep the history of the blockchain as well, right? So the storage space is extremely limited. In practical terms, when I started working in this space, sometime in 2013, the blockchain was 16, 17 gigs at that time for Bitcoin. Now I think it has crossed 200 gigs. So it's like a linear curve, and the size of the blockchain is basically increasing, and they're trying to keep it consistent with how quickly disks are just getting cheaper and bigger. The second thing is that it's very hard to introduce new features into a network, and which is a very interesting dynamic. I don't know if you guys followed like this Bitcoin hard fork. It was a contentious battle for almost 2 years because there are so many different actors involved. So there are the core developers who write the software. Then there are people who run these full nodes. Then there are miners who are actually actively mining on the network. And it's very interesting how different parties have different types of power over each other, right? So that's, in a way, they all keep each other in check. But what it roughly results into at a high level is that if you want to make any changes to the protocol, it's extremely hard to get them through because you have to get buy-in from so many different actors. And that's a problem we looked at, that how can you have this network and still be able to actually introduce new features on top of it pretty rapidly. And one obvious thing is that the writes are very slow, right? In Bitcoin, roughly, they target a new block every 10 minutes. There are other blockchains that try to actually do blocks faster than that, but this is a very complicated thing because you can imagine that there is network latency, there are nodes all over the network, and they actually all need to reach consensus, right? So this latency for slow writes is probably going to stay there due to fundamental reasons, because you want a global network. You want everyone to be on the same state, right? So the writes are going to be slow. Sure, we can do some performance improvements and reduce the latency, but it's going to stay there in general. And then the endless ledger problem is that if you're a new node, you basically, and you don't want to trust anyone else, you have to start downloading the blockchain from the Genesis block, which is the first block, and then build up the history yourself and verify that all of this makes sense. Because in a blockchain, you can actually keep going back in history and verify that all of this adds up to the protocol rules, right? So if I got the Genesis block and I know what the protocol rules are, I can independently verify that all the subsequent blocks actually follow the protocol rules. So I am at the correct state currently in time. Yeah. Yeah, I mean, that's a very interesting game theory problem there, where what's happening, at least in Bitcoin, is that the mining reward, it drops every few years, right? So it used to be that miners would get 50 Bitcoins every block. Now, then they started getting 25. Now they're getting 12.5. But the value of Bitcoin is actually going up, right? So the original designers of the system, they thought that if the value of the Bitcoin is going up, then you're getting like less amounts of Bitcoin, but actually the USD dollar value incentives should still be large. And in the long run, like many decades from now, the mining reward would go down to 0, right? And the idea is that by that time, if the network is like popular enough, just the transaction fees should be large enough that the miners should mine there. But it's a very dynamic system in the sense that if you're not making a profit by mining on the network, you would just like drop out, right? And when you drop out, then the difficulty of mining actually drops. And then there's an incentive for miners to come back on the network, because now it's easier to calculate these hashes because the difficulty of the hash actually reduces. So you can actually calculate them faster. All right, so now we are basically looking at how can you, so we are going back to the original problem. We want to design a decentralized domain name system as one core component of a decentralized internet. And over there, you basically run into this problem that is called Zuku's triangle, right? That if you look at any naming system, the Zuku's triangle basically says you can pick 2 out of these 3 properties. And we can look at them as examples. So a long hash is an identifier, but it's not human readable, right? But you can generate them in a decentralized way, meaning you don't need any central coordination for this identifier. All of you can just generate a public key, right? And you don't need a central party that needs to coordinate that action. So they're decentralized, they're secure, you own the public key, and no one else can, but they're not human readable. Whereas if you look at something like a Twitter handle, it's human readable. I have ownership, but it's because of a central party, Twitter, the company, that can enforce that ownership, right? So it's not decentralized. So Zuku's triangle said that you cannot have all three of these properties, but the triangle was squared by blockchains. So with blockchains, you can get all three properties. And this, the first blockchain that did that was Namecoin, which was the first fork of Bitcoin. Came out in 2011, and it was basically focused on building a decentralized DNS system. So how they do this is that just like you can broadcast transactions for transferring Bitcoins from one address to another, they added new types of transactions. They forked the Bitcoin blockchain, started a separate network, and they said that we can actually include new types of transactions here. One of them is a name register. So there's a detail here where first you announce the hash of the name. Let's say I'm trying to register Muneeb as a name. First I would announce the hash because the transactions are not confirmed, right? So you otherwise other parties might try to listen to what you're trying to register and try to front run you. Like for example, I can send a transaction with more transaction fees and maybe I'll get in an earlier block than you. So initially you just announce this gibberish hash. Once that transaction is confirmed, then you reveal what the actual name was, right? And now in the protocol, because your transaction came first, everyone kind of like can see that, okay, this name was registered by this party, and this is the name now. And later on, you can actually update that name, which is very simple because you have the private key that is the owner of the name, and you're basically signing a new transaction saying that, hey, update my data and association for that name. So Namecoin, what they did was they basically were using the blockchain as a storage layer as well. So any data that you wanted to associate with your DNS like name was literally being written into the blockchain, right? And that's how they built the first system. So Namecoin came in 2011. We released our system, the blockchain name system, in 2014. Initially, we were actually using the Namecoin blockchain. I'll go into that a little bit. And recently, there's this different blockchain from Bitcoin called Ethereum. They've also launched a naming system in 2017. So a lot of people are independently discovering that, yes, human-readable names are important, and building them on top of blockchains gives you this decentralized property. And there are many, many use cases for how people are using these names. So this is what our system looks like. You can go to explorer.blockstack.org. This is like a Bitcoin Explorer. So there are all these Bitcoin Explorers that basically give you information on the network and the blockchain without you running a node. So you can see like what blocks are coming in, what are the transactions being broadcasted there. And this is our version of that for Blockstack. So over here, this is Werner Vogels, the CTO of Amazon, and he got werner.id. So we started new TLDs with our naming system, right? Just like there's .com, .net, .org, we started .id for people, right? So they're getting these Twitter-like handles, and Werner registered his profile, and then in his profile data, he has proofs for basically who he is. So this was basically our identity system, where what we are saying is you register your main username on the blockchain, and then you can actually get attestations from other places that this is you, right? So that's your main identifier, and then you can post a proof on Twitter, on Facebook, on GitHub, on a domain name, and later on we want to actually include attestations from different third parties. Like you can actually get one from a bank or a local government or something where they're saying that, yes, this person is actually Werner Vogels. And the system is adaptive enough to support that. So over here, this is like some summary of like how this name was actually registered. You see the first block where it was registered, when it's expiring. So you can think of blocks as time, right? So we roughly target like a 2-year window for this particular namespace where names expire and someone has to take an action to renew it. And I'll get into like what a zone file is. They're very similar to DNS zone files, but we are using them to put more information there. And because this is a blockchain, all the history is there. So you can actually go back and see like when a name was registered, when they updated certain data, when a name got expired, somebody else registered it. So all of that history remains in the blockchain, and you can go and query it. So as I mentioned that our initial system was actually built on top of Namecoin. These are really early days. Like this is like late 2013, early 2014, and we basically released this system using a namespace. So just like we have these TLDs, Namecoin had this concept of different namespaces. And we basically used that network between March 2014 and August 2015, registered some 33,000 domain names on that network, and sent out more than 200,000 transactions. So it might not sound like a lot, but in the blockchain world, this is actually a lot. We were the largest production system operating on top of Namecoin, and we actually learned a lot of lessons. I'm not going to get into all the lessons, but this was an interesting one. We actually discovered, so in blockchains, the system is decentralized because no miner has more than 50% of the mining power, right? If a single party has more than 50% of the compute power, then you can start doing certain things and start to take more control of the network, right? In cases where, let's say, you have a lot more than 50% of the network, then it's basically effectively you can write whatever you want, because you can even start ignoring other miners and other forks, right? You're forcing it because you have so much compute power that every time you're announcing blocks, that is the longest chain, right? And other people just can't compete with your version of the blockchain. So what we discovered on Namecoin was that a single miner actually had a lot more than 51% of the mining power. That was not the scary thing. The scary thing was no one else noticed, right? Like, so our lesson there was that maybe we need to be on the Bitcoin blockchain that has a lot more production systems running on it, that has a much higher market cap. So if a problem like that starts to happen in Bitcoin, a lot of people notice, right? And because there is a lot of economic activity on that blockchain compared to a smaller network, which was basically built just for this DNS thing and didn't really have that much usage. Other things that we basically looked at was just like network reliability, and again, you know, if a network is actively being used by a lot of services, right, there's a better probability that it will be better maintained. You can read more details about this in our Usenix ADC paper that came out in 2016. But our main lesson was that, hey, can we actually design a system that benefits from the security properties of Bitcoin, right? And then somehow works around all the limitations that it introduces. Because we actually cannot make any changes to the Bitcoin core protocol. No one would accept those changes. It's very hard to actually push them out to life. So this is a Blockstack's architecture. What we are trying to do over here is we are basically saying that, hey, can there be like one security box, like a node that basically when you plug it in, it can be your laptop. It wakes up, it starts processing the blockchain from the beginning, right? And it independently builds up an entire view of the network locally, which means that I have now all the DNS information, I have all the PKI information, so I can actually associate public keys with these identifiers. And then later on, if someone is trying to say, hey, I'm actually Muneeb, I'll be like, why don't you sign a message with the public key that you own, right? And and then you can actually start building up from there. You can extend this to software. For example, if you're downloading something and you want to verify that this came from the right source, again, you have all the public key information locally, and you can start verifying that, yes, this is actually the correct software that I wanted to download. And this is rough. As I mentioned earlier, this basically takes the theoretical trust-to-trust design and actually gives you a real implementation of it. And this is what our architecture looks like. So this is the base layer, the blockchain layer that I already talked about. What we did was we introduced a virtualization layer on top. And the reason for that is that we feel that it's too early in the space to pick a winner in terms of blockchains. Right? Individual blockchains might have certain problems, they might die, some other networks might start, but we want to isolate the rest of the internet stack from failures of individual blockchains, as we saw on Namecoin. So we actually did a live migration away from Namecoin to the Bitcoin blockchain with our virtualization layer. Right? So this virtualization layer, we call it virtual chain. Basically what it does is that it lets you introduce new features. Let's say I want to build a domain name system or something else, right? But basically transactions which are not Bitcoin transactions. And I'm announcing those transactions on the Bitcoin network, but they make no sense to traditional Bitcoin nodes. They're valid transactions with some gibberish data for them. But in the higher layer, in the virtual layer, our nodes, the Blockstack nodes, can actually process those transactions and make sense out of it. So what you get out of the blockchain is linearizability, right? So you get a total ordering of all operations, and once you have a total ordering and consensus on that, you can actually process the transactions and start building, making sense out of them. In our case, it's the history of operations that yes, this name was registered, yes, this name got updated, and all of that information is in the virtual layer. So what we do over here is basically we keep a local database. Now, if you're running a Blockstack node, the Blockstack node is running the blockchain. It could be some other blockchain. Currently, it's Bitcoin, right? So it has the Bitcoin blockchain. It builds up this local database that has the mappings of this domain name is actually owned by this public key, and this is the hash of the zone file, because we don't want to put all the zone file information into the blockchain because of storage limitations there. And for the zone file data, we actually have a peer-to-peer network that I'll tell you more about. So this is what the zone files look like, right? So this is the profile of Werner Vogel's. It basically points to his storage backend, and obviously he's using S3. And what we do with the storage layer is that we treat individual cloud providers as dumb hard drives. Right? Like all these cloud providers, they try to differentiate from each other, and they have their own sets of APIs and various services. What we are doing is we're just looking at them as dumb hard drives, just like I don't even know who's the manufacturer of the hard drive for my laptop, and I don't care. Right? Like if I plug in another hard drive and just copy my data over, it works. This is what we believe the cloud service provider should be like. So we have written drivers for Amazon S3, Google Drive, Dropbox, and a bunch of others. And what that driver does is basically it puts encrypted data on these cloud providers, and it gives you a wide area file system, right? So you can actually migrate your data from Dropbox to Amazon, and it will work because we have drivers for both of them, right? So we just speak their interface and put encrypted data there, so they have no visibility into what this data is. Right? So if for some reason Amazon starts banning all of the Blockstack data, these encrypted blobs that were being stored there, people would start using some other service. Right? So this is how this system is decentralized. Yeah, I think I already went over virtual chains. It's basically one layer of indirection. Right? You can think of that as a virtual machine, just like a virtual machine runs on an actual machine. Our virtual blockchain runs on an actual blockchain. But that's an implementation detail. For all purposes, all the layers on top of our virtual chain think that they're talking to a blockchain, right? So you can think of Blockstack as that it has a blockchain implemented as a virtual machine, and we can actually throw away real blockchains from underneath, right? And that's how we survive failures of individual blockchains. And this is how we do a migration. That this is exactly what we did with Namecoin, that because we have a sense of time through these blocks, you can acquire a lock on a blockchain. Let's say that something happened to Bitcoin, and we announce that by block X, and that block might hit sometime in next month, we are going to stop looking at the Bitcoin blockchain and actually move over to something else. Let's say Zcash, which is a different blockchain, right? So at that point, everyone in the community or people who are running Blockstack nodes, they have a choice that if they upgrade their version of the software, they know that after this block hits, the state on Bitcoin is no longer valid. The state on this other blockchain is going to be valid, and we migrate over all the current state from one blockchain to another. And people might fork. It's like a fork. Some people might say, no, I want to stay with Bitcoin. They can, but usually the majority network is like where most of the people are. So that you'll see a convergence there. Yeah, so if you compare like the name system that we have designed with traditional DNS, you have this recursive query that usually hits the root name servers. Right? What happens with BNS is that This is the peer network, and the peer network is used just for data storage. You're not trusting it for information. You're talking to the blockchain networks, and you're basically building this local database, right? So I already know that Muneeb.id is owned by this public key, and this is the hash of the data that is associated with it. So when I get the actual data, I can get it from anywhere. The peer network is just like one storage. I can actually verify that this data hashes to the hash that I was expecting, right? And so in this sense, this local version of the network state can be in your trusted zone. It can be your laptop. I'm running a node here right now, right? So I don't need to trust anyone else for verifying that I'm actually visiting the right website or talking to the right friend. So one way you can think of like how the system can scale, we're basically looking at two things. One is that just like with traditional DNS, the .uk TLD is actually managed by the United Kingdom. We can have something similar where we can start new TLDs on different blockchains. That's one approach. The second thing, and this feature actually went live recently, is that we can have subdomains, right? So every domain name basically needs to be a transaction on the network, which is an expensive procedure. Right now, I think names cost around 40 or 50 cents, but the Bitcoin fees these days are actually high, so you'll actually end up paying more in Bitcoin fees. But with subdomains, we can actually pack these operations, right? So you can actually register like thousands of subdomains in a single transaction, and that's how we can register more users. Let's say Microsoft wants to register 1 billion people, they would probably like register subdomains and not give everyone a domain name, which is very similar to how the internet works. Like I have muneebali.com, but my wife doesn't have a website, and she would never even make one or buy a domain name. She's happy with her email address or some sort of other identifier on the network. So I mentioned our peer network earlier. We actually experimented with like distributed hash table based networks and saw a lot of like reliability issues. You can read a lot more about them in our research papers, but the system that we have today is basically an unstructured peer network where we have a full replica of all the data. So any node, when it boots up, it basically connects to the peers, and because it has the copy of the blockchain, it already knows what data it's missing. And this is a very interesting property because in peer networks, there's no concept of global state. No single node even knows like what data it's missing, right? So this is very interesting because now, as soon as the nodes boot up, they already know what the global state should be, and they know if they're missing something. So our network nodes, they just keep talking to other peers, downloading the data that they're missing, and the reliability property is as long as there's a single copy of the data on the network, it can be fetched, right? And that's how we have designed our gossip protocol, that we give high preference to chunks which are rare. And you can read more about this in our papers. So this is the full picture, like how the peer network actually works with storage. So you can think of the peer network as like a discovery layer. It basically, first you get the trusted information from the blockchain. Over here, the main thing is that forget about the difference between our virtual chain and the actual blockchain. It's an implementation detail. From the blockchain layer, you basically get trusted data. You trust it because independently you can verify that it's coming from the longest blockchain. Right now, it's extremely hard for any single party, even a state actor, to produce a blockchain that is actually different from Bitcoin and tamper with some data that goes back, let's say, a year or even a few months. Like, you would need so much computing power to be able to produce a blockchain that basically forks away, because as soon as you change a single transaction, it's a different history now with different hashes, right? So you'll have to come up with a longer blockchain that has a different history, and it's an extremely hard attack to do. So all of the nodes can verify that yes, this basic set of data is verified and trusted. Now I'm just going to follow pointers, right? So from the peer network, I'm going to get the zone files, check the hash against the data that I have, and then I'm going to follow pointers to actual cloud storage. The reason we have these two layers is because the zone file data, whenever you update it, you need to send a new transaction on the blockchain, because now that hash needs to be updated, right? So this is anything that is infrequently updated. For example, which storage providers you're using. If you like add a new one or move your data from like one storage provider to another, you'll need to issue an update transaction and update the hash of the data in the network. But then these, at the storage layer, like you can write data as fast as you want, right? Like this is basically like cloud storage, but it's decentralized because you're not dependent on any single party. Like I could be replicating my data on 4 different cloud providers. In fact, this was very interesting that recently Amazon S3 went down, and a lot of services online went down because Amazon was down. And even Amazon's own status page went down because that green and red signs they had for status were images hosted on Amazon S3, right? So, and our system was working because S3 was just one source of data, right? So that was a very interesting real world analysis that, hey, you do need to decentralize these large providers because you're not only dependent on them for like security, but also for reliability. If a provider goes down, it's a catastrophic event in the grand scheme of things. So for all the different limitations that blockchains have, you basically address them like one by one. Like if you're not, yeah, I'm actually going to like go over and try and wrap up. So this is like, I know that we have done research for this project and published papers, but the exciting thing is that it's a real system. It's an open source project. We actually have around like 3,000 developers on our Slack channel, and even more people broadly in the community that are actively working on building applications. This is what the browser looks like if you download it, and this is kind of like the home screen where new apps that people are building gets published here. So it looks almost like an iOS screen that you would see on your mobile device, but this is a browser. So you click on an app, and most of the app actually runs client side, right? So you download the code, and you connect your storage drives, so the apps are writing data to your providers. There's no like remote data that these applications are writing. This is a to-do list app. You can go and try it out. We actually like use the to-do list app to check out items that we are working on for this project. There's a CLI as well. If you download the Blockstack CLI, you can start doing lookups. You can actually start registering names directly on the network through the command line interface. I think this slide is outdated. We have more than 73,000 domains registered on this new internet now. I think which is very interesting because it looks like there's a lot of usage, and this is before we had real apps. Right? So people were basically just curious and they were registering their names, but now we have real functionality. This is something very recent, like last summer, our first apps were published. Yeah, so a lot of people, like all the way from like big companies like Microsoft to small startups, are actually like beginning to use this technology. And recently, we announced a $25 million fund for app developers, which means that if you're an app developer building these decentralized apps on Blockstack, now there's a source of funding for you, where you can actually get some investment from some of the investors that we know who are behind this fund. We do meetups all around the world. I think the latest number I checked in the morning is like we have around 7,000 members all over the world for these meetups. People are basically like coming together because these pain points are something universal. Like wherever we go, like people are like, yes, I know. Like I hate to trust like all these providers. I hate the fact that Facebook has all my data. I want to build a decentralized Twitter, or I want to build a decentralized Facebook. And they don't need to do all the infrastructure work. They don't need to worry about all the libraries that we have, and they can basically just start using them and just focus on their app that they want to write. Clearly, this is not just my work. There are 2 professors from Princeton who are advisors, my co-founder Ryan, and we have a large team of developers. In the next few months, you would actually see the launch of a Blockstack token, because so far, like we've been building different pieces of the infrastructure, but in a way, with the token, you will see the launch of a Blockstack blockchain. And so there will be a genesis block for it, and then the token would be launched, which is something that we are very excited about because it gives everyone in this ecosystem an incentive to be a part of it, right? So all the open source developers, all the different companies, all the apps that are building on it, they kind of like have a small piece of the pie, right? And if this ecosystem becomes bigger, hopefully all of us can actually benefit from that. You can actually go and check out more information on blockstack.org, or more importantly on our GitHub, which is github.com/blockstack. Thank you.